Okay, so this section, we're going to be looking at polarization and bound charges. Okay, so first, polarization. So a polarization, it's a quantity that describes the polarization of the material as a whole. So it's the dipole moment per unit volume. Okay, so capital P represents the polarization of the material as a whole, and P, lowercase p, is the dipole moment of the single atom or molecule or whatever individual dipole moments we have in the material. So let's look at the case where we have a dielectric and it's placed in an external electric field E naught. Okay, so here is our parallel plate capacitor that provides us with an external electric field, and we place our dielectric in between the plates. So what happens is that we get the alignment of the dipole moments in the dielectric because of the external electric field. This in turn induces an electric field because we have alignment of these dipole moments. There's going to be an electric field induced by the polarization of these atoms or molecules. So we have the external electric field that was provided by the parallel plate capacitor. It induces a polarization in the material, and that polarization creates its own electric field that's going to be opposite to the original electric field. Okay, so our goal is kind of to try to find this induced electric field, but we're going to start by finding the induced electric potential in a polarized material. Okay, so to find the induced electric field, first we're going to calculate the electric potential. So we'll start by just looking at a single pure dipole that we assume are in our material. We have pure dipoles, let's say, in our material. And we know the potential of a single pure dipole. We found it in lecture 3.5. Okay, remember from our multipole expansion, the dipole term 1 over 4 pi epsilon naught 1 over r squared r hat dot p. The dipoles in the material, of course, aren't pure, they're physical, but we're going to approximate their potential as approximately equal to the potential of a pure dipole. Okay, so the electric potential of each dipole in our material, we're going to say is approximately equal to the dipole term. So we have each dipole in the material having this approximate potential. So we can rewrite the potential in terms of the polarization of the material, capital P, which is the dipole moment per unit volume. The lowercase p is just going to be equal to the polarization P times the volume element d tau prime. Then if we integrate over the whole volume, we can get the potential of the whole material. Okay, so I've replaced P, our electric dipole moment, with the polarization times the volume element d tau, and then we integrate over the whole volume to get the potential, the electric potential of our polarized material with polarization P. So in order to so this is the electric potential of material with polarization P. If we want to find the electric field from this electric potential, we're going to have to rewrite this integral in a more convenient way. And that's what we're going to do in these two example problems. So you'll be doing example problem 4.1, and I've given you some hints to go about doing that. And then you'll also have to prove that the potential is equal to these two terms. It's the sum of a surface integral plus a volume integral. And going through this proof, you'll see that it's very similar to the example problem we did back in lecture 2, chapter 2, but I've also put the steps here so you can go through those steps to do this proof. Okay, so you'll be doing those. So what we find after you do those two example problems, you'll find that the electric potential of a polarized material with the polarization P is going to be equal to 1 over 4 pi epsilon naught, surface integral 1 over r P dot dA minus a volume integral 1 over 4 pi epsilon naught 1 over r, the divergence of our polarization. So let's look at the first term, the surface integral 1 over 4 pi epsilon naught 1 over r P dot dA. I can write that as P dot n hat, the unit vector perpendicular to the area A prime. So this is similar in form to the potential of a surface charge with surface charge density sigma. If you remember, if you want the potential of a surface charge, it's 1 over 4 pi epsilon naught surface integral sigma dA over r. So we can compare the potential of a surface charge with the first term. We can see they're very similar if we set P, our polarization, dot n equal to sigma b. And so our first term becomes 1 over 4 pi epsilon naught 1 over r sigma b dA. Our second term, minus 1 over 4 pi epsilon naught volume integral 1 over r, the divergence of P. This is now similar to the potential of a volume charge. We want the electric potential of a volume charge with volume charge density rho, 1 over 4 pi epsilon naught rho d tau over r. So in this case, if we set minus the divergence of our polarization equal to rho b, we can rewrite our second term like this. So if we rewrite with these charge densities that we've defined, the polarization of a polarized material is going to be equal to this expression right here, with P dot n hat is equal to r sigma b, and rho b is equal to minus the divergence of our polarization. So we found that the potential of a polarized material is the sum of the potential of a surface charge and the potential of a volume charge. And if we want to find the surface charge, we just do the integral of the surface charge density, dA. You can put those as lowercase. And if we want to find the volume charge, you just do the integral of rho b d tau. And Q surface and Q volume are called, we're going to call them bound charges. Okay, so what are these bound charges? Let's look a little closer. That's the same slide. At the physical interpretation of the bound charges. So remember, if we look back at conductors where we have electrons that are free to move about. If you place a conductor in an electric field or next to, let's say, a positive charge, the electrons that are free are going to move towards the positive charge, and that's going to leave a lack of negative charge on the side opposite to our positive charge here, and this way called the induced charge, okay, where electrons actually were free, they're not attached to atoms, and they can move closer to this positive charge. And that's the induced charge. Even in a neutral conductor, you get this induced charge, okay? In a dielectric, electrons can't move like in a conductor. They are attached to their atoms. But the dipoles in a dielectric do align. So if we take the simple case of a long string of dipoles right here, here's our string of dipole moments with negative and positive charges. We can see that the middle parts cancel out. We have plus, minus, plus, minus, plus, minus. What's left is a negative charge on one end and a positive charge on the other. So even though we couldn't have any electrons move from their atoms, we create a similar situation as the induced charge of a conductor, but we call this a bound charge now, just to emphasize that the electrons didn't actually move from their atoms to create this bound charge. So let's find the amount of bound charge resulting from a given polarization. So if we look at this case of a tube of dielectric material, where the polarization is going to be parallel to the tube, and we want the dipole moment of a chunk put out of the tube. So the dipole moment is just P, the polarization of the dielectric, times V, the volume of that chunk. And in this case, the chunk, let's say, has a cross-sectional area A and a length D. And then we can also find the expression of the dipole moment of the chunk if we say that the charges at the ends are minus Q and plus Q. So the dipole moment is equal to QD. So we can set these two expressions that we got for the dipole moments equal. So you get PAD is equal to QD. So Q is equal to PA. And if we want the surface charge density at the ends of the tube, so the charge at the end of the tube over the area of the end of the tube, we plug in what Q is equal to, what we found for Q, PA over A. Cross out the A's and we get P. So the surface charge density in this case is just equal to the polarization of the material. Now let's say we have an oblique cut, okay, instead of a straight cut for this ends of the tube. The charge is still going to be the same, right, if the polarization is still the same. So P times A. The surface charge density at the oblique end of the tube is going to be the charge at the end of the tube, divided by the area of the end. I'll call A end. Q is still PA, divided by A end. A, this area right here, if we're at an angle theta, is going to be equal to A end cosine theta. So the A ends cancel out. So we get the surface charge density. We cancel out the A ends to just be equal to P cosine theta. So for a uniform polarization, we have the bound charge equal to surface bound charge densities equal to P dot n hat, or P cosine theta. The volume charge in the inside, we already showed that those, if you have a uniform polarization, those cancel out in the middle. So we found, just like we did in the original derivation, the surface bound charge P dot n. Now let's look at a non-uniform polarization. Okay, so for example, here, this material is polarized. We have some charge inside the material and then some charge at the surface. So the bound charge in this case is going to accumulate both within and on the surface for this non-uniform polarization. So the volume bound charge, the negative charge accumulation in the middle, is equal and opposite to the surface bound charge, the positive charge accumulation on the surface, because this is a neutral material. So Q volume has to be equal to minus Q surface. Q volume is the integral of the bound volume charge density times d tau, minus Q surface is equal to the surface charge density dA. Okay, so I plug in what I know the surface charge density is, P dot n. And now I'm going to use the divergence theorem. So minus P dot dA. So you have a surface integral of a vector field is equal to the volume integral of the divergence of that vector field. That's the divergence theorem. So we get our volume charge density is equal to this integral here. So since these two integrals are equal regardless of the volume, we find that the volume charge density rho b is equal to minus the divergence of the polarization. So for non-uniform polarization, we find surface charge density P dot n, volume bound charge density minus the divergence of our polarization. So this confirms what we found in the original derivation of our bound charges. So now what you guys can do is example problem 4.3. You're going to find the bound charges, both surface and volume, for this polarization for this cube, this dielectric cube. And we'll be doing some clicker questions in class. Another clicker question. Another clicker question. And that is it.